No problem. Thank you for the introduction. Good afternoon, everybody. My name is Tsung-Wei Huang, and you can just call me TW. Today I'm going to talk about Taskflow. It's a general-purpose task parallel programming system to help you more easily parallelize the EDA application. And many of you already know, parallel computing or parallel heterogeneous computing is very, very critical for your application performance. For example, if you look at the machine learning today without GPU, or even with heterogeneous parallelism using one GPU, we are able to achieve over 100x speedup over that with CPU alone. So that's the power of parallel and heterogeneous computing. But writing a parallel program itself is not a very easy job because you have to deal with a lot of technical and parallelization detail. For example, you have to worry about a parallelism abstraction, either over software or hardware, and then you have to worry about a concurrency control, task data arrays, dependency constraints, schedule efficiency, load balancing, and even performance portability, and so on and so forth. And there's always this trade-off between what you really want and the cost of that design. For example, everybody wants simple, maintainable, extensible, and portable implementation, but each of that design may steal your application performance a little bit. And I do believe nobody really wants to manage all this technical detail themselves. So it turns out we want a programming solution that can sit on top to help us handle all these technical details and challenges. But why does existing parallel programming system do not work, especially for EDA problem? Well, if you look at many of these EDA applications, they are very, very complicated and very complex. Existing systems, they are typically very good at loop parallelism, regular parallelism, but they are not very strong when things become very irregular, right? Like synthesis, optimization, simulation, and so on and so forth. The other issue is most of the existing systems, they count on directed acyclic graph model that does not allow you to model control flow inside a task graph, like iterative cycle, and so on and so forth. So from the evolution of parallel programming standard, turns out we can envision that the task parallelism is going to be the best model for us to describe heterogeneous workload or parallel computing workload because it captures your intention in decomposing a parallel heterogeneous algorithm into a top-down task graph that eventually can be scaled to different accelerators. So our solution over here is called Taskflow, which was supported by our NSF project to overcome many of the challenges, parallel programming challenges that cannot be efficiently handled by existing system. And the very first challenge we want to overcome is transparency. Okay, so let's take a look at a hello world example in our system. Suppose you want to do 4 things, okay? A, B, C, D. A has to run before B and C. D has to run after B and C. Okay? Each task represents a function or a task. In terms of task flow, this is all you need. Only 15 lines of C++ code to get a parallel execution for this task graph. So first you will need to create a task flow object. Let me see if I can use my point over here. And then you will create an executor to perform the scheduling. From the task flow, you can use in place to insert several tasks in terms of C++ lambda function object like A, B, C, D over here, and use the preset method to relay the dependency between A, B, C, and D. And finally, you can submit the task flow to the executor, and it will perform all the scheduling for you. So at this moment, I believe most of you can fully understand what this code is doing. That's the power of transparency and expressiveness. Another major innovation of our task flow, when you compare with existing system, is our control task flow graph programming model, or CTFG. CTFG goes beyond the limitation of a traditional DAG-based model that does not allow you to express control flow in a single graph entity. For a complicated workload like this example over here, where you have a cycle to describe iterative control flow, conditional tasking, or even a loop, it becomes almost impossible for existing DAG-based system to express a very efficient overlap between control flow and your task. So this is our heterogeneous tasking interface. We have been using CUDA and SQL, so you can write a single source C++ program, and then it will be compiled to run on multiple accelerators like FPGA, CPU, GPU, and so on and so forth. And the programming model is pretty much similar to what you are familiar with the CPU-based model. In this example over here, we have 4 data transfer calls and then data transfer tasks, and then also 1 kernel task to perform the parallel iteration. And you can describe everything in a very similar fashion to our CPU-based model. Using Taskflow is very, very easy. Pretty much all you need is just include our Taskflow project into your project, and you tell your compiler where to find the header file. Because Taskflow is header file only. It's completely written in standard C++. There is no non-standard C++ feature. All you need is to download our header file, include it into your project, tell compiler where to find it, that's it. Everything by default can be visualized. If you want to run your Taskflow program with the visualization result, you just need to enable an environment variable telling the operating system how to dump your execution timeline into the JSON file. Then you can copy and paste the JSON into a browser-based interface to visualize the execution result of your program. And everything is built in by default. We have successfully applied our system to many EDA applications. One of the most important applications we apply is our Open Timer project. If you look at timing analysis, of course, is a very important step in the overall design flow because it helps you verify the expected timing behavior. So if you look at what existing work do, they typically will levelize your graph and perform level by level propagation and use pipeline to parallelize the propagation. But with Taskflow, we are able to model the entire timing propagation in a big Taskflow graph. So we can flow the computation very naturally and more asynchronously across your circuit network, including many in-graph control flow tasks, so we can prune unnecessary propagation on the fly. So this is the sample result that shows you with Taskflow, we are able to achieve over 600 speed up. And of course, that is also part of the reason by using GPU over the baseline with 1 CPU and with 40 CPU, our solution can also be 44x faster. Everything is composable and is unified in our system. Task dependency control flow, they are all associated with each other. So you can represent a very generic control task flow graph and to achieve end-to-end parallelism. And for example, there is a pulse on Rabbit sharing how Taskflow helped their company migrate existing multimedia engine to the parallel target in just a few hours. And the performance got about 8%. So right now, it is open source, and we do have quite a lot of people using that. Some of them are company. For example, I recently gave a talk to Xilinx at AMD. Their Vivado synthesis place and route engine is already using Taskflow. Okay, I believe I'm going to stop here. If you want to understand more details about our system, feel free to check out our website. Thank you very much.
Thank you very much, TW. So, nice picture, by the way. So, questions?
Yes.
So, in your examples, you specified the precedence manually so that A has to precede B and B has to precede, or something like that. But are you also able to figure that out from data analysis, or is that out of scope, I guess?
So the question is about data dependency, and in our system, we do not handle data dependency. It is completely up to application developer. This is probably one of the biggest lessons we have learned when we try to initiate this project, because the way you want to optimize the memory managed data is typically application dependent. So we do not provide yet another abstraction over data, but we just focus on how to describe your workload in terms of task graph, and then we schedule that for you. And of course, you can always describe your data dependency in terms of task dependency.
Thanks.
Thank you. Yes?
More questions?
Are there opportunities in any algorithms you look at for overlapping between data, streaming data between tasks?
That's a very good question. Yes, we do have a very specialized scheduler trying to maximize the overlap between your task and data movement as much as possible. Yeah, but that will be a totally different topic related to scheduler.
Thank you. More questions?
My question would be, how does this language compare or approach to other domain-specific language for data or control data flows, such as Elephant actor language? Because it looks very much like actors you connect in your main program and your behavior, or do you have to provide any analysis with this? Dynamic or static data flow? Because they are domain-specific also analysis for such restricted data flow models of computation that help you to dimension memory.
Yes.
Any work has been done in this area?
Actually, my short answer to this is no. Like I said, we primarily focus on how we can describe a task flow graph, and we can do the scheduling for you. And the reason why we do not want to come up with another domain-specific knowledge is the ecosystem. Because a lot of time when you come up with a domain-specific language, the biggest challenge is you have to convince the community, convince the people to either rewrite their application using your language, or they will start to question about the sustainability of that particular language. So that is the biggest challenge that.
So your task model could be any C++?
Yes.
Object.
Yes. So Taskflow is completely written in standard C++. Like I said, there is no non-standard C++ feature. So it's fairly easy to use and integrate into your project. Thank you.
Thank you. More questions? Okay.
All right. Thank you. Yeah.
Thank you.